Hello everyone. So today is going to be our last video in 6.4. So what I want to do today, hopefully will be a short video, is just to go over some example on theorem 6.4.6, which is what you're going to be asked to do on your next test. All right. So here will be our first example. Let's say we're given f of xy is equal to 1 over x plus xy plus 8 over y. The question would ask you to do the following: find all critical points and use theorems 6.4.6 to determine relative max, relative min, saddle, or the last case is no conclusion. So the question is very specific. You have to use theorem 6.4.6. So let's go for it. So first we're going to find a critical point. So how to find critical points would be gradient of f equal to 0. So let's start with the gradient of f. So gradient of f of xy would actually equal to negative 1 over x squared plus y, and x plus 8 over y squared. All right, so we're going to set that equal to 0, 0, which is a 0 vector in R2. So therefore, tell me the negative 1 over x squared plus y must equal to 0, and 8x plus 8 over y squared must also equal to 0. All right. So once again, we have a system of equation, as you probably expect in this unit. Most of the things that we do wind up having a system of equation, and it is a nonlinear system of equation. So how do we proceed to solve this problem? So I think probably the easiest thing to do is to take the top equation and just say, well, that would tell me that y must equal to 1 over x squared. And then what I'm going to do is I'm going to take this and just plug into the y down here and see what happened. So hopefully this would help us come up with a solution. I don't really know, but once again, these type of questions are difficult to do. So sometimes you just have to try something and hopefully it works out. So therefore become x plus 8 over 1 over x squared equal to 0. So that actually turned out to be x plus 8x to the fourth equal to 0. So that's actually not too bad. So I can factor in 8 and x. Then I have 1 plus 8x to the third equal to 0. So this tells me two possibilities: x equal to 0 or 1 plus 8x to the third equal to 0. So first of all, I notice that x equal to 0 will be a reject, because our original function is not defined when x equal to 0 because of the 1 over x. So that one is out. On the other hand, this would tell me that 8x to the third equal to negative 1, x to the third equal to negative 1/8, x would equal to a cube root of negative 1/8, which is actually negative 1/2. So that seems to be pretty good. Now that we have an answer, now we can go and find y. So y would be 1 over that square. So y would equal to 1 over negative 1 over 2 square. That actually comes out to be 4. So therefore, the critical point I'm looking for is actually this number. So that's not too bad. We only have one critical point. All right. So now the next thing we're going to do is try to apply theorem 6.4.6. So to do that, what I need to do is to first find d. So how do I find d? Well, d is equal to fxx fyy minus fxy squared at the critical points, which in this case at negative 1 to 4. So let's go and try to figure that out. So let's start with fxx first. So we know that f sub x is negative 1 over x squared plus y. and f sub y is equal to x plus 8 over y squared. So now if I take the derivative again, fxx will just equal to 2 over x to the third, and fxy would just equal to 1, which note is the same as fyx. Fyy would actually equal to negative 16 over y to the third. So therefore now I can evaluate this. So at negative 1/2 4, fxx would actually equal to 2 over negative 1 over 2 to the third. So therefore that would be negative 1/8, so therefore become negative 16 when 2 divided by negative 1/8. Fxy is easy, that's just 1, so that's perfectly fine. And fyy would equal to negative 16, over 4 to the third, and that actually come out to be negative 1/4. So now I'm ready to evaluate d. So d would equal to fxx, which is negative 16, times fyy, which is negative 1/4, and then minus 1 squared. So that seemed to me come out to be 4 minus 1, which is 3, and that is greater than 0. So when it's greater than 0, I do have to look at case 1 and case 2. So case 1 and case 2 ask me to identify what happened to fxx. So here I do know that fxx as well as fyy are both less than 0. So based on what we see from the theorem, I can see that this is case 2. And therefore, f has a relative maximum at negative 1, 2, 4. So once you find your critical points, you do have to find the second partial derivative. And once you have the second partial derivative, you just have to evaluate it at the critical points. So obviously for each critical point, you have basically redo this whole thing, evaluate, and then plug into the formula for d to find out what d is equal to. And then based on what d is, greater than 0, less than 0, or equal to 0, you either have your answer directly, or you have to look at one more thing, which is fxx or fyy. So that's pretty good. That was relatively easy. So now let's try another one. This will probably be the last example on 6.4. So hopefully, as I say, hopefully the video will be short. Do the same exact thing, except this time I want to use this function. 3x squared minus 6xy plus 5y squared plus y to the third. So same exact question. Find critical points. Use from 6.4.6 to identify max, min, relative max, relative min, saddle, or no conclusion. So once again, let's go and do our gradient of f of xy. So that would be, let's see, 6x minus 6y. And then that would be negative 6x plus 10y plus 3y squared. And we're going to set that equal to 0. Vector, which is 0, 0. And let's go ahead and solve for it. So 6x minus 6y equal to 0. Negative 6x plus 10y plus 3y squared equal to 0. So it should be pretty simple. The first equation kind of tell me that x and y must equal to the same thing, because otherwise that would not be able to satisfy it. So if that's the case, I can go and say that, well, my second equation basically just tell me that negative 6y plus 10y plus 3y squared equal to 0, because I just replace x with y. So now that I can solve. So I'm going to try to solve that. That becomes 3y squared plus 4y equal to 0. Factor in y. And now I can see that y must equal to 0, or y must equal to negative 4 over 3. And since x and y are the same, this means x equal to 0, and this means x equal to negative 4 over 3. So we do have 2 points. So critical points in this case would be 0, 0, and -4 third, -4 third. So that would be our critical points. Now let's try to find D. So to find D, I'm going to have to do fxx and fyy and fxy. So I'm going to go ahead and do f sub x, which is 6x minus 6y, and f sub y, which is -6x plus 10y plus 3y squared. So fxx would just equal to 6. fxy would equal to -6, which is the same as fyx. And fyy would equal to 10 plus 6y. So we have two critical points, so we're going to go and try to do this. So at 0, 0, fxx is going to be 6, fxy is going to be -6, and fyy is going to be 0. Oh, I'm sorry, 10. By putting 0 for y, I get 10. So now we can do D. So D would equal to fxx times fyy minus fxy squared. So sim to me, that is 60 minus 36 would come out to be 24, which is greater than 0. And we know that fxx and fyy are in this case both greater than 0. So therefore, tell me that f has a relative minimum at 0, 0. Now let's do the other one. So at -4 third, -4 third. I think that's the correct critical point. Yes, it is. So what will happen in this case? Fxx is still 6. Fxy is still -6. And fyy will be the one that gets changed. So it becomes 10 plus 6 times, let's write that down, 10 plus 6 times -4 over 3. So that come out to be 10. So that's 2. So 10 minus 8 is 2. And so now I'm going to do D. So D would equal to fxx times fxyy minus fxy squared. So that becomes 12 minus 36, which is equal to -24, which is less than 0. When it's less than 0, we actually don't have to do anything. We know immediately what happens. So f has a saddle point at -4 third, -4 third. There you go, and that's it. That's the last example I want to show you. So both of these examples kind of illustrate what you have to do. So first you find critical point using gradient equal to 0 vector. And then once you do that, you find the partial second order partial derivatives, fxx, fxy, and fyy. And then you evaluate that at the critical points, and then based on that and compare that to theorem 6.4.6, the 4 cases, and you'll be able to figure out whether you have a relative max, relative mean, Sando, or no conclusion. And that's it. That's how this kind of problem works out. All right, so that's it for this video. I will talk to you on the next video or in class. All right, bye-bye.